Welcome to this special session on the Towers of Hanoi problem. This is part of the course on software constructs and tools and the section on problem solving theory and applications. In the earlier sessions, you have seen how a problem can be tackled in a general way, how it could be broken into smaller parts, how an algorithm can be made, what are the characteristic features of an algorithm, and so on. This session is a special one on the Towers of Hanoi, which is an illustration of both a recursion and an iteration process for coming to a solution. During the course of this session, we will give you the origins of the problem. We will show a model to explain what the Towers of Hanoi looks like. We will run an applet to illustrate what kind of time it takes to do the problem, and then we will talk about the algorithm and relation to binary trees and other aspects of computer science. The legend around the problem is that in the eastern areas, monks have 3 towers on which sit 64 golden rings. The monks are moving these rings from one stack to a third stack using another stack in between. At the beginning of the universe, the legend goes, all the 64 rings were stacked on one tower with each ring smaller than the one beneath. As we go on, as the monks keep on working on the this, they move this to the third tower with each ring smaller than the one beneath, and the legend has it that when all the 64 rings are moved, the world will come to an end. This clearly shows that the time required to make all the 64 moves is a very large time, and we will see this as we see the approach towards solving the problem. A more accurate history of the problem in terms of computer people is that a French mathematician designed the game in 1883. The game was called the Tower of Hanoi. Some authors also use the expression Towers of Hanoi. Both the Tower of Hanoi and the Towers of Hanoi are used with almost the same frequency in the literature. To see what the problem looks like, we need to go over the rules of the game. In order to show what the rules of the game are like, we have with us a model which shows a number of disks which are kept on 3 pegs. Now, the first rule is that initially all the disks are on one peg, as is shown over here. The disks, as you can see, are on a pattern where the smallest disk is the top and the largest disk is at the bottom. The next step in the rule is that only one of these disks can be moved at a time. You could move this over here, or you could move this over here, and so on. There is a third rule, however, regarding the movement, that a disk can be placed either on an empty disk, as I have done, or on top of a larger disk. So this disk cannot be placed on top of this one or on top of this one. However, the smaller disk can be placed on top of a larger disk. Now, given these constraints, the goal of the game is to move all the disks using the smallest number of moves. Now, as these number of disks grows large, the time required is increasing exponentially. So I'll show you how the problem is solved with a smaller number of disks. Now, if we take just 3 disks and recall the rules that were there, we have to move this from this peg to this one using this as a spare pole. Obviously, the first thing we have to do is to take the one at the top. We take it to another place. Then we take this one, put it at this place. Then we put this one over here. Then we can put this large one over here. Then we put the small one over here. We put this one over here. And then we put this one over here. So it took us 7 steps to carry out the process. Now, what happens is that, as you would notice, that if the number of disks is larger and we can, for example, take more disks, then it will become more and more difficult to do the job. With 3 disks, it took 7 steps. With 4 disks, it takes a larger number of steps. With 5 disks, it takes even larger, and this does not go in proportion to the number. Now, to show how this happens, it would be very time consuming to do it on this model. We have therefore for you a simulation which is based on what is called a Java applet. As you go in this very course itself, you will learn about Java programming, and eventually you will also learn about Java applet programming. So we have here for you an applet which shows this Tower of Hanoi problem, and we begin by resetting the thing. Now, if you look at this simulation, it is exactly like the one that we had over here, but it can run much faster. You can adjust things and so on. Now, we have over here, for example, a button which adjusts the number of rings in the game. So if you click on this, you get larger and larger number of rings. You can do on the negative side and reduce the number of rings. Let us now repeat quickly the one for the 3 which I showed you, and we will have the speed a bit slow so that you can observe this, and let us look at the solution. Now, he's done exactly what I had done. Now, the important thing about this problem solution is that it took 7 steps to do it for 3 rings. We can reset it, have 4, again auto solve, and you can see that this takes now a larger number of steps. Now, actually the whole problem runs around the concept that if you can move the ring at the bottom to the bottom of the 3rd peg, then the problem is of 1 dimension less than the earlier problem. So when we are looking at the solution for a problem with 4 pegs, we can see that it is like solving 2 problems of 3 pegs. If you want to solve a problem with 5 disks, it is like 2 problems of 4 disks. When you want to solve a problem with 6 disks, it is like 2 problems of 5 disks. And accordingly, if you keep on increasing, and we'll go back to the applet and show that if you look at a larger number now, we have 5 over here, and we can again solve this, and you can see how many steps it takes. We'll make this a little faster so that these things happen, and you can see the number of steps that it took. Now we look at the next thing, that is 6, and again can run it in an auto solve mode. You can see the number of steps it takes. Now, if you were to watch these steps carefully, you will see that at each time it is being made out of repeating the same kind of a thing, but for a different number of disks. So the structure is that of a binary tree, with which you've probably heard of in some other context. So we'll now look at the summary. What is the pattern that emerged when we ran this Java applet? And when we ran the applet for 3 disks, the moves required were 7. When we ran it for 4 disks, the move required were 15. When we ran it for 5 disks, it was 31. And you can quickly see that a pattern is emerging. And the pattern is that the minimum number of steps required for n disks is 2 to the power n minus 1. For 64 disks, it therefore becomes 184, 467, 440, 737, 09551615 moves. Now this is a very large number of moves, and even if you were to make a move at 1 second per move, and you saw that when I was doing the demonstration on the model, it definitely took a larger amount of time. You take 589, 942, 417, 400 years for so many moves at 1 second per move. Even if you went at a lightning fast speed and used a microsecond for a move, 1,000th of it, you still see that you are talking of something like 600 million years before all these moves could be carried out. So this then is the exponential rate at which the growth of the problem happens when we are looking at the number of disks that are there. Now, in order to be able to move further, if you want to construct a solution for this problem, you need to start looking at what is the recursive behavior in the problem. For this purpose, it is useful to look at how the problem got divided. As I said, that if I had a disk, 4 disks to begin with, and somehow I could put the largest disk in the third tower, then I would have a problem with 3 disks. Now, you see that what is shown in this chart is that you can have a 4-disk problem and it gets broken into 2 3-disk problem, and a 3-disk problem gets broken into 2 2-disk problem, and a 2-disk problem gets broken into 2 1-disk problem. So the number of steps required you can count by counting all the 1s on the lowest line. That makes 8. Now the number of 2s in the next line, that's 4, that's 12, and then the 2 3s, that's 14, and the 1 on top, 15. So it's 15 steps required to solve the binary tree, which has a depth of 4. We can also in a sense see this, this is said in another way, that the problem of size 6 splits into 2 problems of size 5, problem of size 5 splits into 2 problems of size 4, a problem of size 4 splits into 2 problems of size 3, and a problem of size 3 splits into 2 problems of size 2, and a problem of size 2 is actually no problem, it just splits into 2 problems of size 1. Now, having said this, it is now important to be able to raise this to a level of abstraction. It is one thing to solve a problem on a model where you take a few steps and do something and show it. It's another to have an applet which runs and demonstrates the solution, and it is the real job of the computer person to find out what exactly is the algorithm behind it. And once you know the algorithm behind it, you could write a program for it in any suitable language. It could be Pascal, it could be C, it could be C++, it could be, of course, Java, because you've shown the applet in that, and you could have various ways of approaching towards that problem. Now, much of the material related to this will be available on the website which is supporting this course, where you will be able to see the code for solving the Towers of Hanoi problem in different languages. But what we have over here is an analysis of the issues which arise in this problem. The algorithm, if you will, gets divided into really 2 parts. One is what we would call the Tower of Hanoi procedure, and the other is what is called the transfer disk procedure. Now, the Tower of Hanoi procedure really is a procedure which says that do this for n disks and do the same thing for n minus 1 disk. But then when you are doing this for any number of disks, you have to have some procedure laid down according to which the disks get transformed or transferred between the different poles. So if you look at the first part, that is the Tower of Hanoi procedure. So how would it go about? So you describe the algorithm by first establishing a number of disks. So you say n is so much. You have to say which is the original pole, where the things are stacked up in the right order to begin with, which is the spare pole, and which is the final pole. And your algorithm therefore says if the current problem is n greater than 1, then recursively you call the function to transfer all disks except the bottom disk from the current original pole to the spare pole. Then you transfer the bottom disk from the original pole to the final pole, and then you recursively again call the function to transfer all disks from the spare pole to the final pole. And then, of course, finally you transfer the current disk from the original pole to final pole. The transfer of disk itself requires you to label the 3 poles. So you have what is called the original pole, you have to label the final pole, and you have to label the spare pole. And there's another way of looking at it, and that is that if you saw the pattern, especially when the applet was moving very rapidly, every alternate move involved the transfer of the smallest disk from one pole to another. And if we imagine that these poles are in a circle and the disks are numbered from 1 to n, then all odd numbered disks are rotating in one direction and all even numbered disks are rotating in another direction. You would have noticed when I was doing this thing on the model that sometimes the smaller disk went to the final pole and sometimes it went to the spare pole, because this depended upon the sequence and the number at which it was placed. We have a briefer statement of the same algorithm. You could say that on odd numbered moves, move the smallest disk clockwise. On even numbered moves, make the single other move that is possible. You notice that because of the rule 3 that a larger disk cannot sit on top of a smaller disk, there are certain things which cannot be done. You have to choose only the smaller disk and take it on to the other one. We are overwhelmed with the kind of information related to the towers of Hanoi that is available on the internet. In the course material which you will go on the website, you will get a lot of references to the web. You will be able to see many of these examples, but I would still like to draw your attention to some of the demonstrations and examples that are available on the internet. There is an HTML version for 4 disks which has been made available by Andrew Cumming. Again, the site address will be given in the course material. You can go through this and see each of those steps involved in the transfer of 4 disks, which is then viewable by any browser. There is also a VRML version of it available, so you can get a dynamic feeling of the movement of the disk as it goes from one stage to another. However, you may have to install an appropriate plugin, and you will first have to download the file and then only be able to work on it. There are many other solutions also possible of the towers of Hanoi problem, and almost every programming language from Pascal to Fortran to C to C++ has been adopted for this purpose. What is listed for you in the accompanying slide is that it is available in Fortran 90 to show that even Fortran 90 is capable of recursive procedures. There is an ADA program. ADA was a language which was very popular with the Department of Defense, and even they worked out a program to show the towers of Hanoi. There is a program in C which is used to instruct robots how to play the towers of Hanoi. So instead of the kind of applet where the disks move by themselves, you can have a game where there is a robot who actually moves these disks, and the instructions to the robots have to be the solution of the towers of Hanoi problem, and there is a code available in C to do that. Having gone through much of the actual way of solving the algorithm, the relationship binary things, there is a modern version of the legend also which is coming up. And the modern version of the legend in this web-centric society therefore relates to the internet. Just like the original legend I talked about in the beginning related to monks in an Eastern environment, the new legend says that there is a website. There is a website on the internet, and every time somebody visits the website because of some shock being given to somebody or whatever, one of the 64 disks is made to move following the rules of the game. The rules of the game are exactly the same which was said earlier, and when all the 64 disks have been moved, the website will be destroyed, and at this time the internet will also be destroyed. The whole point is that all these legends really talk of time durations which will be very, very long. The importance of the towers of Hanoi is such that there are many other related problems and issues which have come up. We've given you an example of n number of disks and 3 pegs or 3 towers. But suppose you had a larger number of towers, the task would of course become easier. If you had arbitrary number of disks and arbitrary number of towers, would you be able to give a general formula to say what happens? Is there some such equation available? These are some of the other questions that arise. So when the number of towers is more than 3, what would be the procedure? Is there an algorithm for any number of towers? Is there an equation determining the minimum number of moves required for various number of disks and towers? Also, there is an important question of proof. For example, we've shown this that the 3 disk solution took 7 steps, 4 took 15. How are we sure that this is the minimum number of steps in which it can be done? Could there be an alternative, shorter procedure? Across this curriculum, we have emphasized that while we are teaching computer science, while we are talking about solving problems with the help of computers, there are certain common skills which cut across the curriculum. And these common skills, you will notice, are as important in the Towers of Hanoi case as in many other situations. The first one is on the statement of the problem itself. When we try to say that we are describing the problem, you will notice that you have to specify the rules, whether we specify it in 4 rules or we need more rules. Do we need to specify diagrammatically? Are we clear in our statement? For example, if we had forgotten to say that a disk can be put only on top of a larger disk and not even when a stack is empty, the statement would not be very precise. And when we say that a larger disk cannot be put on top of a smaller disk, isn't there a redundancy? Can't we simply say a disk cannot be put on top of a smaller disk? So there are issues of communication over here where in terms of the statement of the problem, we want to be precise, not ambiguous, but also quite complete and not leave out something. In terms of documenting the solution, again, it's one thing to demonstrate it on a model. It's another thing to run an applet to show the answer, but how do you describe what is the answer? We have shown already a number of ways of saying the solution: the model, the applet, the algorithm, the binary tree, and there could be many other representations. There is reference to the VRML representation. So which of this is a superior way of documenting the solution? The next point there is appreciating the size of the problem. We showed that as the number of disks increases, the number of steps required increase exponentially and not linearly. And finally, when you have a number of possible solutions, you have to benchmark these solutions for appropriateness. Whether the use of a programming language is important. We said you could use Pascal, C, C++, Ada, Fortran, anything. Is it the processor that you use that is important? Is it the kind of a distribution between memory and execution time which is important? And benchmarking different solutions gives us the training that is required to choose an optimum solution for an actual information technology application case. In terms of summarizing, therefore, what have we learned today? The first thing that we've learned today is, although the legend about the problem is thousands of years old and the problem itself is 100 years old, there are still aspects of the problem which are being explored. There is a paper as recent as February 1999 which talks about attempting to find a faster algorithm to solve the Towers of Hanoi problem. This is a classical example of a recursion procedure. A recursion, for example, like factorial n is n factorial n minus 1 is well understood and rather simple. But to take a problem which is put in the context of a puzzle or a real life situation and then to put into a recursion process is something which is quite illustrative and educational. Similarly, the fact that although recursion may be a simple way or a more obvious way of solving a problem, you could actually have non-recursive ways also of solving the problem. We showed that there is an iterative way of solving the problem which is not necessarily using recursion. So these are some of the lessons that we have learned. New faster algorithms are still being proposed and opportunities for solving this problem exist in almost all programming languages. So it is not only an illustration of the power of one programming language or the latest and most fashionable programming languages, but almost every programming language that the computer industry has had has been used to attempt the Towers of Hanoi problem. We hope that you will continue to explore the materials given on the website, the web references, the exercises, projects and assignments associated with this, and find that the whole experience about Towers of Hanoi has been quite exciting and interesting. Thank you.